fine, right? So we basically try to simplify the problem by guiding us in how many parameters we need to put for each one of the polynomials that we have to identify. The R, S, and T. We understood the idea. At the end of the day, we find ourselves that we are using the inverse of a model. And if we have perfect model following, then it means that we have the identification of A and B 100%. But most importantly, what we found in the configuration that we have seen yesterday is that the feedback loop is supposed to work and minimize the small errors that you have between your estimated model and your model. Right? So the feedback loop is trying to correct this difference. And the controller is composed of two parts. I'm going to put it here maybe. So we said this is BM over AM. This is my reference model. This is my reference signal. My YM comes here. Then we have Y that comes from the other side. It goes through S over R. It goes through A over B here, B over A, and then it will generate Y. And then we have at the middle here, we have this term that will be multiplied by the inverse. And the inverse, I'm going to write it in a different color because it's.
So when you said the reference model, it does mean the one that we're going to the one that we find with recursive or LRC or.
This one is based on your specification. This is your reference point. And then we are going to have here A over B. So I'm putting A over B in different colors because these are coming from your estimation.
Yes.
This is your physical system. All right? So we have two components in the controller. We have a feed forward. And we have a feedback. So the feedback loop is supposed to correct this small difference that you have between Y and Y, or the difference is due to the fact that you don't know A and B correctly. There is a small.
Sir, I have one confusion here. Our model is B upon A.
Yes.
But our estimated model is the inverse of A over A.
When we estimate the model, in this model there are two terms.
Yes.
There is the B and there is the A. So what we estimate is also B and A.
Yes.
So what we get is B hat and A hat. Huh?
Yes.
But when we implement it in the controller, we put the A over B hat. They are two polynomials. They are inverse.
Yes.
So your question is?
So it's on us that we are replacing here as an inverse.
It's a polynomial. Your controller is telling you, your control method is telling you this is the way you have to use it.
Because the polynomials of B is representing the zeros of the system.
Sir.
And the polynomial of A is representing the poles of the system.
That's right.
And in our estimated, it's also the same. The polynomial of A is
See?
representing the.
But it's your estimate. It's not another transfer function. And A over B, it's not one term, it's two terms.
Yes.
So you when you put your algorithm of estimation, and my algorithm of estimation, I will put it here. This is my least square method. And this least square method will generate for me an estimate of A, an estimate of B,
Yes.
and then I will use them here to make the inverse.
So it's our algorithm. A.
It's our algorithm. This is your controller.
Yes.
All this is your controller. This is your controller. This is your controller. Okay, good question. So everybody is okay with this?
Yes.
All right? So the inverse model, we are using it to close the gap between Y and YM. And then the feedback is taking care of any errors in the estimation. And we understood yesterday that if I design my controller by inversing the dynamic, when I say my controller, it means I design R and S and T by looking to the inverse of the zeros that are bad, then S over R would be unstable and the system would be completely unstable. Is it clear what I said here? All right. So there are other things that we need to add in order to help us with the way we are going to design. So last time we put some inequality, less or equal, but during the work, we are estimating, we are saying, what if we are at the limit? What if we are at the limit? For example, we said that degree of S is less or equal to n minus 1. Degree of R should be bigger than n minus 1. So this means that we put ourselves at the limit, at the boundary of n minus 1. We fixed the degree. So the way to fix the degree, we are going to put it based on these conditions, and we call these the compatibility conditions. So the compatibility conditions, we are going to select the reference model, the same degree as A. We are going to select the degree of BM, the same degree as B. And then degree of A0, of course, it will be equal. It will no longer be inequality. Everything will be at the limit. So we call this the compatibility condition. So how the algorithm works? The algorithm works as, if you want, a function where you submit the value of A and B. So this is the data that you are going to put at the input level. You submit the value of A and B. From these conditions that we verify, we check if your B and BM are the same degree as A and B, degree of A0, if it's compatible with this equation. Then we separate BM and B minus times BM prime. And then we are able to apply it directly to find our controller. So we decompose B and B plus times B minus. We generate a solution for L prime and S according to this equation. We generate the solution for T as A0 times Bm prime, like what we did yesterday. And once all of this is defined, then I can find my control input U. So the output of this function will be U, right? Which is T over R times U reference minus S over R times Y. I take this U and I apply it to the system. I will get Y. I will get an estimate, new estimate of A and B. I will call this function again. And I will go directly again. So this is how it works.
How it will stop until the estimation is in the
It will
difference
stop?
between.
It will not stop. It's your control. You are continuously under control of the system. Unless you stop the control, it automatically.
I mean the estimation part. Even the estimate.
We don't stop. It's done based on the clock. So they have a clock of this, and we have a clock that governs the estimation. I talked about this one time, Sahih. I told you that most of the time we use them the same clock, but in certain systems we don't identify all the time. So we have the control every 0.1 second, but the other one maybe after every 1 minute or 5 minutes or whatever, we do estimation. But in the transient, during transient period, you need to be able to estimate your values. You cannot wait 5 minutes with an estimate that is wrong, for example. Huh? You remember, this is the least square method that you are going to apply here. Least square method, recursive least square method, because we are going all the time, has to start with the initial values. The initial values of P0 or P, and the initial value of your parameter theta. So if you are going to start with any initial value of parameter theta, then you need to probably make a condition. Unless the error is less than something, you should keep always at the same frequency as the controller. Once the error is within a reasonable limit, then you can relax the estimation. Is it clear what I said? It makes sense? All right, so now we are going to start the fun part. So suppose that you have a system like this. So this is 1 over S plus 1. This is your plant. This plant here. But in continuous, and we said we are going to work in discrete. So to work on discrete, I need to transform this system and I need to transform the system based on a sampling frequency, sampling period, 0.5. Now, if you do the simplification of this, the transformation of this system to discrete, using, for example, C to D conversion from MATLAB, using 0.5 second as your sampling period, then you are going to end up with a system like this. This is B, and this is A. Everybody is okay with this?
Is it hard to do it without MATLAB, like the method that you show us, that S equal to exponential?
This is why we showed you the method, so you can do it quickly.
Okay.
You can do that, at least to get the feeling of what is going on, and after that you can use some softwares to do this. Everybody is okay with this? Yes?
Because you said MATLAB sometimes give you a complex model, and
Yeah.
if you use there is another method that you show us, it will give you less complex.
MATLAB can give you three ways to do the continuous to discrete conversion. Either you use Paul matching or use Taussian approximation, which is basically the exponential approximated twice, or you can use Euler method. Huh? So these are methods that you can use based on the complexity of the system that you have. So still MATLAB can be very useful
Yes.
unless there is a system that you cannot handle, square root of something complex. When we have a square root, we say that the system has bifurcation point. So in complex domain, there are many trajectories crossing each other. So there is not only one single trajectory like this one. So at that time, then we need to pay attention. طيب, two things that I would like to bring to your attention to. This discretization depends on the sampling period. You observe here the time constant of the system is 1. And the sampling period that has been selected is 0.5. This is half of time constant. And during the time constant, you are going to get only 1 or 2 points, right? The first and the second. This is during the time constant. If you assume that the system will go to 95% of its output, so 3 time constant, then you are going to get 6 points. And this is really not that much. It works, but not that much. Normally, you have to target the frequency that will give you enough points. But you cannot target the frequency that is very, very fast, which means h very, very small, because at that time you are going to make your system completely busy with making the identification and trying to find the value of the base. So there is kind of a compromise. Trade-off. This point clear? All right. The second point, we look to the system here, and when we solve for the system, I will show you later in the slides. We have a 0 that is finite, but the 0 is negative. Right? So we put here q, this one equal to 0. If q is equal to minus this element divided by 0.165, so it's a negative. So it's in the it's a negative.
There is no minimum.
Sorry.
There is no minimum phase problem or something.
This is negative, but it's in discrete. So you have to bear with me here. Negative in discrete means you are on the other side of this half of the circle. It's 0.09002 divided by 0.165. So this one is very less compared to this. So you know that is less than 1. So it's within the circle, but negative. It's a stable 0, but negative. Everybody is okay with this? Yes?
So there's sometimes even the poles are the unit circle, but sometimes they have some bad effects.
Yeah, I will show you this thing. Just give me 1 second. I will show you this. Now, according, yeah.
Doctor, in our system now,
Yeah.
we have a sampling time for the estimation. We have a sampling time for the controller itself. How many outputs do we get? Does it depend on the sampling time of the estimator or the controller?
So now to simplify our analysis, we are going to say we have the same sampling time.
Okay.
So what will be the question?
No.
Why?
But because the controller is like every 100 samples per second.
Okay.
And the estimation gives me like in this 1 second give me like 2 estimations only.
Two estimations.
So now I will get 50 output, 50 values twice. or I want to get 100 values of y.
Yeah, but 50 values y, but they are very close to each other. So it's like the same value. So you know, for example, in Aramco they have what we call the data compression. They have some software they run, but they don't take all the points. So what they do, they put the limit, upper limit, and lower limit like this. So if they get the value here, so unless the next value is out, they will keep the same value. They will not change it. So so you see here the values like this. They are all this one.
Okay.
They compress the data. Okay. Do we want to use compressing data? No, in the identification. So this is why I told you, let's assume that it's the same frequency. What is your question? So if the number of estimates that I'm going to get from A and B, I can make a logic. I will say reset A and B every 10 seconds. You understand what I'm saying? But at that time, I need to pay attention because recursive will not work. It has to be more sophisticated algorithm. Any other question? Any other question? All right, so according to our compatibility conditions, we said that BM has to be the same degree as B, and AM has to be the same size as A, right? The requirement to find the value of AM is that zeta is equal to 0.7 and omega n is equal to, I forgot, maybe it's in the next slide, let me check. The value of Wn is equal to 1. Okay, this is the value of the requirement. So from here I can compute s squared plus 2 zeta omega n s plus omega n squared. I can assume this is my BM over AM continuous. I convert it to discrete, and I will get the value of BM that is shown here. The value of AM that we showed here. Everybody is okay with this?
Just when you give us this in time domain, is there our real plan that we're going to estimate based on this, like the response of this plan?
Yeah. This is our reference model.
Okay.
Our reference model. We don't have to go to continuous. You can use e to the power s capital T. You know that we are able to compute S1. There are two poles. S12 is equal to minus zeta omega n plus or minus j omega n square root of 1 minus zeta squared, because zeta is less than 1, so it has to be complex. And then I will use e to the power s capital T, or in this case e times s times h, and this will give me z1, the two poles in this case. I can program it this way. Now Bm has to be the same degree as B. So the simplest thing I can generate is that Bm is equal to a constant multiplied by Q. Right? I don't have to have another constant here. It's useless to have a constant, so I can come here and say my Bm is equal to a constant multiplied by Q, and now I can select the value of this
I want
constant.
to eliminate the 0.
So how to select the value of this constant? This constant multiplied by Q, alpha times Q. How I'm going to select alpha? Am I clear in what I'm asking you?
Yes,
and what
yes,
I'm doing?
yes.
Yeah? So what would be the value of this constant?
Depends on.
What would be the straightforward way to find this constant? Constant times Q. Huh?
I'm not getting it.
You are not getting this. Okay. Which part? So I can repeat it. CTE is a constant. It's the abbreviation for me for a constant. Alpha. Alpha times Q. So the question is how to find this alpha. So we can put alpha times q plus alpha 0. Because it's here, the only condition you have is that degree of Bm is the same as degree of B. Degree of B is coming from the system. My assumption is the system has a degree of 1. So I'm going to use Bm with degree of 1. Now the simplest way is to use Bm, sorry, not B. Bm is equal to alpha times q.
Yes.
How I'm going to select alpha?
But why we don't add the constant? We make it a general first order system. I mean alpha q plus.
General makes it more complicated. Alpha q is be more than
Close to this number, 0.09 divide 0.1.
which one?
Close to this number. And opposite.
0.09, 0.1 divided by 0.09.
Yeah, because this
If you compute 0.1 divided by 0.09, it will be around
minus 0.8, so I need
28 something. Huh? So it's not this.
We calculate from omega and z.
From the sometimes when you do the block placement, you have some steady state error.
So
So we need to calculate the this alpha based on the error that 1 over the DC gain.
this is your reference model. So what steady state error you want to see in your reference model?
0.
0. So alpha will compute it from the steady state requirement. What will be the value in continuous? If I want to compute the steady state requirement, what should I do?
Not just
Omega
put
ends.
put some step without the gain that, and then the final value of the response of the same equals, I'll just reverse it. One over that.
Because how to find this value? If I give you a transfer function, how you compute the steady state?
the final value.
How to compute the final value?
Limit when s equal s goes to infinity and z goes to zero.
No, s to 0.
S goes to 0.
Usually in MATLAB just
Yeah.
put the step and get the final value.
As equal
Hello?
goes to zero.
MATLAB gives you the final value like this.
One of
Ah,
the-
you put the test,
Z,
yani.
z equal to 1 goes to 1.
Z equal to 1. Anybody knows why Z equal to 1? Or in this case, Z is represented by?
Z
Ah,
Yeah,
the
z
gain
equals to
the gain
1
of the
to get,
discrete system
T
is 1.
Final.
because e to the power
Ahsan.
0.
Because e to the power 0
Zero.
times h makes Z equal to 1. So if I want to compute in discrete, what should be the gain of the steady state? The gain of the system in steady state, I need to replace Z by 1. Right? So if I go and replace the system by Z by 1, here Q represents Z. Right? Everybody's okay with this? Q represents Z, so I have to replace Q by 1. If I replace Q by 1, I will have 1 minus 1.2305 plus 0.4966. What should be the numerator?
The same.
The same.
The same.
To have again the ratio 1, so steady state equal to 0.
To zero.
So this is how to compute alpha. So we compute alpha by making sure that Bm over Am has a steady state error equal to 0. Why we want steady state error equal to 0? Because in our control we are making UC multiplied by Bm over Am, and we want to get Ym, the exact value of Ym, not 2 times Ym, 3 times Ym. So the steady state equal to 0 in terms of values, what we want in terms of desire. Everybody is okay with this? So this number 0.1761 is computed to find the ratio between Bm over Am, giving you 1. The final value. Is it clear? So we found it ourselves. We said how to find alpha. Alpha, we go to steady state. This is the other requirement because I gave you zeta and omega n only. Steady state error, we would like to have it equal to 0. In order to make it equal to 0, in continuous s equal to 0. In discrete, s equal to 0 means q equal to 1. I replace by q equal to 1. I should find the ratio equal to 1. Okay? So the ratio equal to 1 will give me a steady state error equal to 0. From here, I have done my Bm over Am. I'm done with it. Everybody is okay? The next step now becomes the analysis of B, because B, we said, it has to be decomposed on B minus and
B plus.
B plus. So I take 0.1065 as a factor, and I take whatever left, and I analyze if the zero is in the region that I want or not in the region that I want. But already I know that 0.1 is part of B minus, right? Because B plus is monic. So here we go. Our pole, if we try to compute minus 0.09, we will find it around minus 0.8. It's in here. It's stable within the circle of 1. However, it's equal to minus 0.8. Now, if it is equal to minus 0.8, we said z is equal to e to the power s capital T, and I have z equal to minus 0.8 e to the power s capital T from both sides. Everybody is okay with this? Yes. Now, when you look to this, normally if we were working on real systems, the exponential is always positive. It can never be negative. Right? So in order to match the two, we are going to say this system can be written as 0.8 multiplied by e to the power j multiplied by
Bar.
pi. Right?
Yes.
So we write it in phase mode. In phase mode, this is the amplitude of the signal, and e to the j
Minus.
times pi,
Minus.
it's minus 1. And in fact, it could be either plus j times pi or minus j times pi. Everybody is okay with this? So I have two possibilities. Either it is plus j times pi or minus j times pi, because the cosine of pi or the cosine of minus pi is always minus 1. It's the same point in the circle. Everybody is okay with this?
Repeat.
Repeat again. So we are looking now to B again, and this is very important for us. We look to B. We have to decide about B. Does B has poles? We said in our analysis that B can be decomposed in B plus and B minus, and we said in B minus we put all the bed of B, the constant and the zeros that are either damped or they are in the right hand side. Everybody is okay with this? So I computed the zero, I found it minus 0.8. Your friend computed before, it's around minus 0.8. So it's minus 0.8, this is Z. I would like to see what is the pole in continuous, because I would like to understand what is the dynamic. Is the dynamic something that I like or something that I don't like? So if I put minus 0.8 equal to e to the power s capital T, the matching between the two, if I was really working on real systems, not complex systems, I cannot put e to the power st equal to something negative. So what I will do in order to make sure that I am compatible in terms of writing, I will write this as, complex numbers can be written as a plus b times j, or can be written as amplitude, which is square root of a squared plus b squared, times e to the power g times theta, the phase. So here, since there is no sign, it's a real term, then it's only cosine. The cosine can be pi, and the cosine of pi is minus 1, or it could be minus pi, and the cosine of minus pi is also minus 1. So I can say here this number can be written either as 0.8 times e to the
Or minus
j times pi, or 0.8 e to the power minus j times pi. Now it makes sense?
Yeah, I understand this part, but just one question. In the 0.8, we choose it because of the.
How did you find 0.8?
Divide 0.9 over 0.1.
Exactly.
0.09.
So basically what we took this number divided by this number. So
Oh.
Q is equal to minus this number divided by
Divided.
this number. This is the zero. That gives us minus 0.8. Now I need to find what? S. Because S is going to explain to me what is going on in terms of dynamics. We are very familiar with continuous, but with discrete we did not work that much. So we would like to understand what is happening when the zero is minus 0.8. So if we take the log from both sides, what I will get,
Len 0.8.
S capital T
Yeah,
is equal to len
0.8
0.8
plus
plus
Len or G bar.
G bar. Right? Which means that your S is equal to len of 0.8 divided by capital T plus J pi over T. We agree with this?
So Dr. for the Q, so we are going to divide the next B over the previous one. B1 over B0, right?
Yeah, basically you are trying to solve 0.165 times Q plus 0.0902 equal to 0. So, and this will give you the value of Q. This is the Q that I'm trying to find here. This will give you Q equal to minus 0.0902 divided by 0.1065.
That's what I
Yeah, exactly. But everybody understood this? So basically, if you look at it in the complex plane now, you will do this maybe one time, and after that you will be okay, huh? But at least you know from where it's coming. When you do this in the complex plane, what you will see is that we have the real part equal to len of 0.8 divided by capital T. The imaginary part is pi over capital T. And then the pole is here. The zero is here. Which means
Stable imaginary.
stable imaginary. What does it mean, stable imaginary?
It has
It has oscillations.
oscillations.
It will create oscillations. Right? And now we said B minus will have to contain all the bad zeros. And the bad zeros are either underdamped zeros or zeros that are completely unstable. For this system, it contains a zero, which is stable zero, but the zero will create oscillation. And here is your judgment. You can decide that this is acceptable. You can decide that this is not acceptable. So the first time we are going to do it now, we are going to assume it is acceptable and see what will happen. Everybody is okay with this? This is zero, yes. This is the value. This is where your zero is. Here. Right? But you know, in continuous, you cannot have a complex number only one.
Yes.
So this is why we said it's also the same as minus j times pi over capital T. It will generate exactly the same zero. Right? It has a complex conjugate because the zero is here. Yes.
We start from the continuous and then convert the transfer function to discrete, or we started from the discrete.
Right now we started from continuous. We converted to discrete. We found the zero. We came back to the system. Maybe this is a very good point.
Because why don't we just do this analysis before the starting?
This is an excellent question. Why we don't do the questions before we convert to discrete and do the analysis? Right? What will be the answer?
Because we are going to work after in discrete.
What will be the answer?
What's the question?
Your friend is saying why we did not do this analysis. Right now what we did, we took continuous, we converted to discrete, then we looked to the zero in discrete. I converted back to continuous so we understand what's the problem of the dynamic. And now we continue the design. We are going to continue the design. But your friend is saying why we went back and forth, discrete, then back from discrete to continuous.
The system identification uses discrete.
We know the system identification uses discrete, we have to use discrete system. What else?
Because S domain, it's easy to understand what happened. It was right or left hand. But
Same.
in Z domain, just we have circles.
Circles and
So
it's more
we
difficult.
confused.
We
Because
will
any change of value, it's a big challenge.
The question, the real answer is In continuous, there was no zero. There was no zero. The zero has been created by your discretization and your sampling theory. Everybody understood that?
Yes.
This is a very important point. So you are expecting your discretization to create dynamics for you. And these dynamics, this is one of them, which is the zero. So this is why we went to discrete, and in discrete we noticed there is a zero. We computed the zero, we found it's negative. We said, let's go back and then see what's the meaning of this. But as I told you, do this only once. What you will do next is that from now on, you understand that any zero in the left-hand side, negative, will create oscillation. You don't have to make this calculation again. What will be the value of the oscillations? You look to these curves, these circles, right? You see these half circles like this?
Yes.
These are different zeta. Zeta is the damping. So if you look to minus 0.8, minus 0.8 is before zeta equal to 0, which is minus 1, and zeta equal to 0.1.
Under damped.
Circle, it's about omega n or zeta, because omega n.
This is omega n, these one, right? This is the value of the omega n, right? These are omega n. These circles are about zeta.
About zeta.
So this is zeta equal to 0, which is the circle of 1. You're,
It's more resolution.
yeah, you are completely imaginary. Huh? You are completely on the imaginary axis. This the curve for zeta equal to 0.1. This is the curve for zeta equals 0.2. And here, when you are in the positive, zeta is more than 1 and above. Now, when you look to 0 as minus 0.8, you know it's going to create Fourier oscillations. If you want to see how much these oscillations, you look to the zeta that is closer to the zeros. In this case, the zeta that is closer to the zero is the zeta equal to 0.1. This is your zeta. So the system will, or the zero that you are going to create will create for you a damping equal to 0.1. So oscillations that are closer to 0.1
Under damped.
under damp system. Make sense what I'm saying? Or?
And you will see if it's acceptable or not.
I will see if it's acceptable or not. What will be the impact of my assumptions? Assuming it's acceptable for me, I would like to go and see what will happen. It's zero at the end of the day.
If it's not, what we will do?
If it's
It's not because this is
If it's
our,
not, then we go back to the design table and say we should not ignore it. We should take it into account as something that is not, it's something that we don't design. This is what design, design is about, yes.
But if the ball or zero in imaginary axis or any imaginary axis, it's exponential decay, decrease as exponential. For example,
Yeah.
it's there.
Right. It's
How
going
we
to,
can find this exponential?
the exponential
Yeah.
is zeta omega n. Omega n for you is pi over t. See omega n here?
E to the power minus.
E to the power zeta, which is 0.1,
Yeah.
multiplied by pi over t. Is it clear now how to read this curve? Clear for you how to read the curve?
There is some discontinuity between 0.1 and 1.
There is not discontinuity, but there is, if you want, you can have more curves, but you will not be able to read the whole.
Not the more curves. For
Ah.
example, if the outer circle is representing 1, zeta equal to 1.
Zeta equal to 0.
Zeta equal to 0?
Yes.
Okay.
Because you are in the imaginary axis. Imaginary axis means that you are complex, completely complex conjugate. There is no real part, means zeta equal to 0. System completely not damped. Zeta equal to 1 is this part. This is zeta equal to 1. Only the half of the circle on the right side.
So what about this n? What is it?
What?
N. The n. N3, N4, N5.
And where is the 3 and 4? Ah, the n.
What are they?
Well, يمكن harmonics. These are harmonics that you have in the signals because they are multiple of this pi over here. They are harmonics. Yeah. I don't remember, but I think this is what it is. Yeah.
Initially, when we look at the system was 1 upon S into S plus 4. There was no zero in the system.
No zeros.
We convert it into the discrete.
And then the zero appears.
The zero appears. So this zero appears due to the sampling period or sampling time.
Yes, the sampling time and due to the method of discretization that we are using.
But initially we don't have any zero.
We don't have zero. Yes.
We created our own zeros, or it is a real dynamic of our system.
This is a good point. Your friend is saying this zero, is it real dynamic or is it due to the discretization? This is
Yes,
what you're saying.
because if I change the sampling time, then maybe there will be more zeros.
It's
or-
due to the way we discretize the system. The dynamic that you have, if you want to do pole dynamic matching or for zero matching, we have two poles, one at zero
or a zero.
and one at minus one. So if I do the pole zero matching from continuous to discrete using e to the power st, I will find 1 over z times z minus 1 times z minus e to the power s minus 1 times t, based on the e to the power s capital E. But this is one possible value of discretization. Another way to discretize this is we say that we have two poles at infinity. Two zeros at infinity. 1 over s squared is also 0 at infinity. S equal to infinity, so I would like to replace this in the top and see what will happen with s equal to infinity. Another thing, like what we did here, we come and we add the q minus 1. There are many techniques, and you have seen this maybe in your bachelor degree. There are 3 ways to do this. Either you keep it as a constant, or you add q, or you add q minus 1, and all of them are valid. The way we use discretization in MATLAB gave us the 0. So in the discrete, this 0 is a dynamic that is there. In discrete, 0, this 0 is a dynamic, is a valid dynamic due to the discretization. Right? In continuous, we may not find it. It's not there.
So in discretization, it may have effect, or
has
we are seeing the zero.
Yes.
But in the continuous system, we are not seeing any zero.
We will not see 0. There is no 0.
But there is zero in the system.
There is no 0 in the system. It's coming from your discretization.
How zero hold?
Huh?
When you hold.
The
when
zero,
you-
zero, zero order hold.
Yeah,
Yeah,
zero order.
this is zero order hold. It
Zero
adds
order
0
hold.
minus 1. So
Can we say if we make our sampling time close to 0, maybe the oscillation gets less? or something?
yeah, you can try it. We will try it later.
Computing will be harder.
Huh?
Computing will take longer. Makes very small sample.
Yeah. You need. Sometimes it's not worth it.
Because 0.5 is so big.
So big compared to time constant. But this is your selection. It's some, before it used to be dependent on the hardware, still now dependent on the hardware that you are going to put. So if you would like to buy something cheap, you would like to have a frequency that is not that very high. So the sampling frequency would be big, and then you have to pay the price for that. Yes.
Is there difference between the oscillation due to zeros and oscillation due to modes?
Pause. Yeah, there is difference between the oscillation between poles and the oscillation between the zeros. Right? Dynamic will be, impact will be different. It's like you have s squared plus 2 zeta n omega n plus omega n squared in the numerator. Is it the same as having it in the denominator? It has an effect. I showed you last time adding 1 0 what will happen, sir? I gave you 1 over s squared plus 2 zeta omega n s plus omega n squared, and we told you if I use zeta equal to 0.7, then the overshoot will be 5%. Then I add a 0 in the numerator, 0, stable 0, and the zeta of 0.7 will give me not an overshoot of 5%, but an overshoot of 20. You can Google this, the effect of zeros on the dynamic of the system. It's available in the book of Dorf that I put in Blackboard. If you go to chapter number 4, you will see the effect of the zeros on the system. Any other question? So all these are valid questions, huh? Because when you are going to design, you need to think about all this. What is going on with the system? But this calculation that I did with you and put pi over t, blah, 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 is just to make sure that you understand what this figure represents, right? So this figure represents, you see omega n equal to pi over t? We have pi over t here. This is your omega n, right? So any zeros that is on this axis, even if it's single, 1 0. In continuous, it will generate 2 zeros, one conjugate, two conjugate, because you cannot have one only complex. And then it will have omega n frequency of pi over capital T. The zeta for this particular zero depends on which value of curves you are closer to. Right? Here we are closer to 0.1, so it's almost 0.1, the value of zeta. But it's between 0.1 and 0, the real value. So it could be 0.09, for example, as value, or 0.08. What I said here makes sense?
Yes.
So now we are going to say, let's assume that this is acceptable. We agree with this? So if we assume that this is acceptable, this is our first assumption. If we assume that this is acceptable, then I'm able to write B as equal to 0.1065 multiplied by Q plus A0, or whatever we can call it here. We can put 0.8, huh? Right? And then when I decompose B in B plus times B minus, I can say that B plus would be equal to Q plus 0.8 because harmonic polynomial, and then I accepted the 0, I said it's okay. And then B minus would be equal to
Constant.
0.1065. We agree on this? Okay? Everybody? Yes? Yes.
We write P0 is equal to 0.106 or multiply of this. Like this is like what we did yesterday, and the calculation that we did for.
Yeah, we did the same yesterday. Some examples. I don't remember what we did yesterday. I think that this is we did some examples on continuous and discrete and how we selected B plus and B minus. So B plus, we said it has to be a monic polynomial. Monic polynomial means the highest
Yes,
degree is 1.
I don't have problem with this. I mean, like how we write it, or like that, 0 point.
Is it 1 plus 0.1, Q minus 1,
Yeah.
or Q plus 0.8? At this level, Q plus 0.8 is fine. You don't have to write it as function of Q minus 1. Any other question? Am I going fast? Clear? Not fast? No? Okay, ready. Doable, feasible. Compatibility conditions. We have AM, we selected the second order system. So degree of AM and degree of ADR equal. Degree of BM and degree of B 1, so equal. So these compatibility conditions are satisfied. Now we need to know what's the degree of A0. So degree of A0, based on my analysis, it says degree of A0 is equal to, according to this formula, degree of, what is it? I don't see it, now you have to tell me. Degree of A, what's degree of A? 2. Degree of A is 2. Minus degree of
B plus.
B plus 1.
degree of B plus is 1. Minus 1, which means
0. It's
0.
constant.
So we don't need A0. A0 is a constant, but it's a monic polynomial. So since it's a, so we don't need it. It's 1. So A0 is 1.
Oh, sorry.
Yes?
A0 was, this was the correction polynomial.
Yes, the observer. So here A0 is equal to 1. Alright? So we are done with A0. Then it says you need to find R prime and yes, degree of S. We are going to take it to maximum. So degree of S is equal to n minus 1. So which will be equal to 1. So this implies that S can be written as S0 times Q plus S1. Or vice versa, depending on what we are going to write it later. Everybody agrees with this?
Yeah.
So you see now why we said last time that we should not take all the range from 0 up to n minus 1, because if we take from 0 up to n minus 1, we are going, in this case of course it's 0, it's 1, or it's 2, huh? but it's 0 or 1. But we will have many possibilities if n is equal to 10. We fix ourselves to one value. And in this one we have two parameters that we need to find. Right, two parameters of S, S0 and S1. We said also that degree of R is bigger or equal to n minus 1. So since I selected degree of S equal to n minus 1, I can select also degree of R equal to n minus 1, which implies R
1.
Is equal to degree of 1, so degree of R is equal to 1,
Let's say R0 plus
which implies, right, so this is the degree of R that you are looking at. So degree of R is equal to
R0 cube.
we said that R we are going to decompose on R prime multiplied by B plus. Since the degree of B plus
It's 1.
it's 1,
So
so R prime will be
0.
No, 1, 1,
Degree
1.
of R prime is
Yes.
1.
The degree is 0.
But after, we can just say it as 1.
1.
Yeah, the degree is 0.
So can you repeat why R prime is equal to 1? Why you said R prime equal to 1?
Degree of B plus is 1.
Degree of B plus is 1.
So degree of R plus needs to be 0 in order to be.
Degree of R prime is 0.
Yeah, then we can just select 1 as the R prime as 1. Constant.
Constant. It can be constant, but we selected 1. Why it cannot be 2, 3? Monic polynomial. Monic polynomial. We are okay with this? We are okay with this?
So in theory, based on what you discussed yesterday, R is supposed to have a larger or a higher degree than S, right? Or equal to.
Yeah, it's bigger or equal to.
So,
So it's selected equal to.
theoretically speaking here, we could choose a power of R that's greater than this,
Yes.
for example, right?
We can. There is no issue. But the more we selected the bigger number, the more it will be complicated for us. So this is the minimum degree design. Now comes the work. I'm going to assume we have B over A, and we know the value of A from the previous slide. I'm going to assume A as equal to Q squared plus A1Q plus A0. What is A1? What's A0? Parameters that we have already, right? So A1 will be equal to minus 1.6065 and A0 is equal to 0.665. The reason why I call them A1 and A0 because I don't want to repeat again every time 1.6, 1, 0.6, 0 and 1, etc. And I'm going to come to this one and then say AM will be written as Q squared plus AM1 times Q plus AM0. Right? Whatever. You can call them semi 1, semi 0, Ali 1, Ali 0, nobody cares. And then what's the value of AM1? Minus 1.32. What's the value of AM0? It will be the last value that we are looking for. Now, based on this, I am going to go to my equation that we have. Where is the algorithm? Yeah, this algorithm. Let me go. The algorithm say A times A prime plus B minus times S is equal to A0 A. So I'm going to write here A, which is S squared plus A1Q plus A0 multiplied by R prime, and we said R prime is 1 Q squared. Thank you. Did you put S there? No, yours. So why there is nothing here?
Because one.
Because 1. R prime is equal to 1. This is the R prime. Right, so here we have 1, if you multiply it by 1. Plus S0Q plus S1, or S1Q plus S0 if you want to follow the same nomenclature. So you'll be consistent. We are going to put it like this. Nobody cares, but we can put it like this. S1Q plus S0 multiplied by B minus, and B minus is equal to 0.1. 0.65. This is equal to
A0 is 1.
AM.
AM, because A0 is 1. So Q squared plus AM1Q plus AM0. You agree with this? So this I'm going to write it equal, and I'm going to rewrite this equation down here. Right, so this will be Q squared plus A1 plus S1 times 0.1065 times Q plus A0 plus S0 multiplied by 0.1065. Everybody understood from where I got this equation?
You have to find this.
So this equation is coming from this equation that we have in the top here. Anything not clear in my writing here? Everything for you is not clear. Nothing is clear? Like, what should I do next?
Equate.
This one and
1 is equal to 1. We are done.
this.
This has to be equal to AM1.
AM1.
And this has to be equal to
AM0.
AM0. This is the
We
graph
have
is
to
good. We have how many parameters to find?
2
What are the unknowns?
is unknown.
S1 and
S0 and
S0.
S1.
S0 and S1. These are our unknowns. Right? So we are going to write A1 plus S1 times 0.1065 is equal to AM1. And then we have A0 plus S0 multiplied by 0.1065 is equal to AM0, which implies that S1 is equal to AM1 minus A1 divided by 0.1065. And here it implies that S0 is equal to AM0 minus A0 divided by 0.1065. Am I done?
There is R. What about R?
T.
There's T.
T.
Yeah.
So we are left with T. And T is equal to
A0 B.
T is equal to A0 multiplied by
Yeah.
Bm prime. And the value of Bm is equal to Bm prime B minus. Do we know Bm?
Yes.
Yes. So Bm is equal to 0.17 something multiplied by Q. So So Bm is given here. It's equal to Bm0 times Q. So I'm going to write it as Bm0 times Q. We have Bm0 times Q is equal to Bm prime, I don't know. B minus is equal to 0.1065. Right? So 0.1065 multiplied by Bm prime. Everybody's okay with this? So I'm able to find Bm prime equal to Bm0 divided by 0.1065 multiplied by Q. You agree with this? From here I can conclude that T will be equal to Bm0 divided by 0.1065 multiplied by Q. This is the value of my We agree with this? Are we done?
I think yes.
We have R, S, and T, and we are done with this case. What I did, anything clear first? Yes. Anybody has any comment about what I did? Anything that I went very fast, it's not clear? Yes.
How we select the value of R prime as a 1?
Why?
Why, yes. It was a monic polynomial, but I didn't understand clearly.
Okay. We said that the degree of R is equal to n minus 1, which is equal to 1 because n is equal to 2.
Yes.
And R is equal to R prime multiplied by B plus, which means that the degree of R is equal to the degree of L prime plus the degree of B plus. What's the degree of B plus? 1. So 1 equal to degree of L prime plus 1, which means that the degree of L prime is 0. So it is a constant.
Constant. Okay.
Why we selected equal to 1?
Monic.
Monic polynomial.
Does this method ensure a stable R? Because we have a stable R.
It is stable R. It's going to be a stable R.
In general.
It has to be stable R because you are making you have your reference model and you are not inversing the unstable zeros if you want. Right? So unstable zeros we are not including them in R. It makes sense? Yes? Yes? I know it's Thursday, the weather outside is really nice.
Yes.
Beautiful. Any question before I go to MATLAB? Then MATLAB is now simple, right? So I did 2 programs for you in MATLAB. The first one that I'm going to use will be I need to use for you one simple one first, and then after that we'll make it a little bit more complicated. So are you able to see the writing here, the code? Shabazz? Yes? So in the code I put here the sampling period, 0.5, as we said. I took the transfer function, which is 1 over s times this plus 1. Is it clear, the writing? Yeah? And then I converted the system from, in fact, this one is just to write it as a numerator denominator with different numerator and denominator here. I discretized here, continuously discrete G and H. Then I identified all my parameters. What is B0, what is B1, what is A1, what is A2, right? So B0 and B1, B0 times Q plus B1 on the top. In the bottom you have A1 Q squared plus A1 cube plus A2. Then I took my specifications, omega n equal to 1, zeta equal to 0.7. I created my transfer function, which is omega n squared over s squared plus 2 zeta omega n plus omega n squared. I converted to discrete. I extracted the numerator and denominator. Then I changed the numerator to make sure that the numerator has a gain equal to 1. The system has a gain equal to 1. If you do this in MATLAB, due to the frequency that I used of h equal to 0.5, you will also have a 0. And the 0 is not Q, it's something else. So I ignored the 0, I replaced with my 0. And my 0 is 0.1762 multiplied by Q. Then after that, I generated extracted the value of Bm and Bm1 and Bm0, which means the numerator coefficient of my reference model, and I extracted the coefficient of my reference model denominator. All right? Then,
Doctor, why you divide with 1?
Sometimes
Then minus.
they don't give you one and
sometimes the
before
first-
the square. They don't give you one.
Yeah.
that gives you something else.
What's beta?
Beta, just to correct, make sure the gain is equal to 1. Well then, beta is here. See, it's the inverse of AM1 in the AA2 divided by B0 plus B1. So make sure that the gains are the same for both systems. Then I compute what should be B plus, what should be B minus. In this one, this is another example. I'm so sorry, but B minus and B plus. I should not use this one. Maybe this one. This one, there is the. Yeah, this is the one. This is the one, okay. So I selected B plus equal to Q plus B1 over B0, and then B minus equal to B0. They're exactly the same thing that we did here. And then Bm prime, of course, is equal to Bm divided by the value of B0. Yeah. And then I compute all the thing, and then I put a step here, and I plot whatever is happening with the system. That's it. This is the design. Assuming that I know the value of B and A, they are known for me. So if I run the system here and I see what will be the performance, since I said I know the exact value of B and N, they are known for me. Then we get what you get here is the plus are the reference model, and the circles are the response of your system. So they are whatever they are.
Yeah, because it's.
Because I know the system perfectly. It's a perfect model for the system. Very perfect one. You are okay with this? So now I'm going to add the identification and see what will happen.
Yes.
Right? So I'm going to go back to my code. And need to look to this one. So here, what will happen? I need to add the estimation part. I'm going to estimate the value of A and R in every loop. So what I need to identify how many regressors I have, how many parameters I need to identify. So I need to identify 4 parameters, 2 in the numerator, 2 in the denominator, for B and A. Everybody understood why 4? 2 coefficient of the numerator and 2 coefficient in the denominator. So this is 4. I selected lambda equal to 1 means that I'm not forgetting anything. So this is every value of time has exactly the same equal weight. I use it P0 equal to 100. This is,
we don't trust our.
I have a little bit of trust. Not that big, but little bit of trust. Otherwise, I need to take it very big. Then I took an initial value of theta. And the initial value of theta that I took here, you can see it's very far from the real values. -2, -1, 0.01, and 0.01. What I did make sure of, however, is that the denominator is stable, so it gives me zeros. The poles are within the circle. But the numerator, I just put anything. Then I took the initial value for these coefficients, and I started my loop estimation. Of course, here loop estimation, when you look to your difference model, since you have q squared, then at that time you need to write it as q to the power -2, etc., and make the time shift in your domain. So the time shift will give you this. It will give you m1 of I minus -2 minus -1, etc. So yi of I minus 1, this is here. Then you have yi of I minus 2 plus ui of -1 and ui of -2. This is just my way of coding. We generate the value of phi. We compute the value of k for the least square method. We know that now. We know how to implement the square method. We compute the error between my estimate and my real value observation, and I update the value of theta. And then once I get the value of theta, I compute b plus, I compute b minus, and then I compute what will be the controller values. Then from there, I generate the value of t. I compute the closed loop system. I compute my control, and then I come back to the beginning of the loop. I introduce my control there. So if anybody will ask me what are the steps of your code, I will tell them first step is estimation of A and B, because my method of design requires for me to know A and B. So I cannot start designing without A and B. I start by designing A and B, and then I do exactly this algorithm that we did. Exactly the same thing as it. And then I iterate with the same frequency. Once I'm done, then I plot everything. Is it clear what I said? So if we run it here, we are going to see what is going on with the system. These are the estimate of my parameters. Estimate of B. So we have the green one is your exact value. This curve is your estimate with the least square method. This line is the exact value, and the red one is your estimate. So you see there is a transient where your estimate is very far from the exact value. This is for B. And then for A, it's the same thing. I can see that A starts here from the top and goes to the exact value. And the same thing starts here at the bottom and goes to the exact value. And I converge. In all the parameters, I converge at a certain time to the exact value. Up to now is okay?
Yes.
So during this transient of the estimation of my parameters, the A and B that I'm using are not the correct one. They are still in transient. They are still in transient. This is the control signal. Right?
Yeah.
The control signal is like this because I'm using step change as an input. So in fact, maybe I should start with the step before I go to the control, because by itself, the control is very significant for me. This is the output. So I put a stair step. The green one is my reference model. It's very slow to update. This is here. So the blue one is your reference signal. So I put a reference which is the staircase. You are okay with this? The green one is your ideal model. This is your BM over AM. This is how the system behaves. This is your YM. The red one is the output of your system. So you see here, I start with an error between the two. Especially here, you can see the difference between the model and the reference. It's not a perfect model following. Then the more you go, the more there is a correction. Until at a certain time, you will get
Yeah.
the perfect model following because you converge in terms of parameter of estimation. Alright?
So on the horizontal line, this time is in the seconds, no? 0.
Yeah, it's whatever, seconds. Unit of time, seconds. So if you zoom on one of these, so if I zoom on this part, for example, here, you can see the difference between your reference model and the real system. Huh? And this is, you see here, the values are incorrect. Your parameters are not the right values because you are still in transit in the identification. You have an error, but you see the system is trying to correct with S over R. The S over R is trying to bring you close. Yes, but it's not enough. You're still having error. You exceed, you come back, and once you achieve your parameter converge, then you see the error here is almost zero. So you have perfect model following once you converge in terms of parameters. And the signal is beautiful. The output is beautiful. So let's repeat again what we did. We estimated the value of the zero. We found it's equal to minus 0.8. We said that this will introduce oscillations, but we will accept it part of B plus. Accepting it part of B plus means that we put it in R, because R is equal to R prime times B plus. So B plus R contains the zero that is the oscillation. And R is in your controller. So the output of your control is this. So you understand now why the system is giving these kinds of oscillations? Because of B plus. Because of the value of B plus that you just assumed it's okay.
Can we consider this as chattering?
It's not chattering because the chattering is normally on the state, in the output. This is oscillation in the controller.
But this will affect our actuation.
It affects your actuation. So basically, if you have an airplane, you will see the flappers doing this all the time
Yeah.
in order to keep you stable. So what you see at the output is a very nice signal.
But
Your airplane is really does beautifully well. But in the back, this is in order to keep you on this level. You understand what I'm saying here? So imagine that if there is an unstable pole there, what will happen to the control?
So stable.
Huh?
Stable.
You don't fly this afternoon, huh? Everybody understood? So we call the system here, the control is ringing. Ringing means it's giving me oscillation. And these oscillations are due to the...
You can see it as an aggressive response of the controller.
Huh?
You can see it as an aggressive response of the controller.
It's not that aggressive, but the controller is trying to compensate for the oscillation created by the zero. Because the controller is trying to do whatever he can.
So it is acceptable.
If it's for you acceptable, it's acceptable. You are the designer. Somebody will come and say it's not acceptable. You are going to break their plane after 2 or 3 flights. Okay? Somebody will say no. You know, in the airplanes they have a log for every flight. So even if the pilot arrives and safe and everybody is happy and they go home and you are eating your dinner, there is people there. They will go through the log file to see what the pilot did during the flight and how the airplane behaved. So if they see that he did some maneuvers where he exceeded some of the limits that are not tolerated by the company, they will give him blame. Right? Because all the signals are recorded in the system. Somebody will go with a data recorder and download all the data, the flight from the system. What I did here with you is okay? It's clear? Make sense? All right. This is fun, right? I will stop here for today. What I will do with you, inshallah, next time, we are going to come back to the sixth example and we say, this is not acceptable. I'm going to put the zeros in B minus.
Ramadan, Dr. Muhammad said has a problem with
That's a problem.